Right, let's see how I can do on this next lesson in geometry, which is the excircle. Now, I'm a little apprehensive. This is not difficult, but everything depends on how well I can draw the diagram. So let me have a go. But needless to say, this is a wonderful topic taken directly from Geometry Revisited, and you'll get a nice diagram and a nice derivation from the book. So this is just to give you an idea of how this is going about. So let me try drawing the diagram. Like I said, let me make some space for myself, and let's try to draw an acute angle triangle, which is also an arbitrary triangle, and what we already know is that if I take the angle bisector and another angle bisector from here, then this point is the in-center. So please note that this angle and this angle is same, and this angle and this angle is same. Now, we already proved that if I draw a perpendicular from the in-center, then all these three sides are equal. And last time I made an attempt to highlight the fact that this particular line bisector might intersect at a different point from this perpendicular. Just to quickly remind you, this distance we proved last time. For example, what should we call it? Let's just call this as x, y and z, and this point b, c. Now this distance ax was s minus a, and this was also s minus a, and so on. Now let's see a very beautiful construction. So at this stage we're going to introduce something new, which is the excircle, and it comes out very easily and naturally. What you need to do is try to construct the angle bisector of B. But this time it is the external angle bisector of B. Let's do the same thing for C. Now, I just in anticipation and also I know that okay, just let's see this point. If I extend carefully, let's do this. Let me just I told you I'm going to struggle with the diagram. Now this particular line, if you extend, okay, so let me draw the bisector of angle C, but from the external angle, and this angle bisector of C, the external angle here. Now look at this point. This is a very interesting point. Let me just call this as IA. Now IA is the intersection of the external bisector of B and the external bisector of C. But it has some immediate, very nice properties, and that is straight from the angle bisector theorem. If I take the perpendicular distance of this point from this line, then because it's the angle bisector, the perpendicular distance of this point from this line will also be equal. So these two lengths will be equal, because IA lies on the angle bisector of this angle B. So let's just call this as RA and RA. But because IA is also on the angle bisector of C, the perpendicular distance of this point from this line will also be equal to RA, and so all these three lengths are equal and I'm calling it RA. And immediately please notice, or maybe just wait for some time. Now what we will do is we will keep our compass here and take the radius equal to RA and draw a circle, and now you will be easily convinced that okay, I think we can do one thing immediately before this. Notice that this point is equidistant from this line. I don't know what to call this. Okay, let me just call it L1. And this point is also the same distance from L2, which means that this point lies on the angle bisector of A, and therefore in anticipation of that I have already extended the angle bisector here and made it pass through point IE in my construction. But now you are convinced that my construction is correct. So I repeat, this point being equidistant from this line and this line lies in the angle bisector of angle A, and therefore this line, which is angle bisector of A extended, passes through IA. Okay. So now, like I said, I keep my compass here, take this equal to this radius, and this circle is definitely going to be tangent to this line and this line and also this line. And I think I've gotten away with my diagram being reasonably nice. So I'm pretty happy about it. So we'll say to the rest. So you can see that this line L1, this line L2 and this line L3 are tangent to this circle, and this is our excircle. By symmetry, you will also get an excircle opposite the vertex C, and get another excircle opposite the vertex B. And right now we are looking at the excircle opposite the vertex A, and that is why it has been named as IA as a center with radius RA. So with this picture here, we'll be able to write down one or two nice interesting formulae. And that is, we still got a long way to go for this excircle. So now we will make some simple observations. And what are these simple observations? Let me just get to it. So what I want you to notice is that this, let's name them now. What shall I name them? I just call this as maybe X dash, Y dash and Z dash. I first want you to notice that line L1 and line L2 being tangent to the circle, I just want to write it here. AX dash, look at this picture here, AX dash is equal to AX dash is equal to AX dash is equal to AZ dash. AX dash is equal to AZ dash, and that is the reason is they are tangent segments. So that's the first nice calculation we are making, that these two lines L1 and L2 being tangent to the circle, AX dash is equal to AZ dash. The second thing is that because line L3 and L1 are also tangent to the circle, this length BY dash is equal to BX dash. So these are also tangent segments, and similarly on this side C y dash is equal to C z dash. So let me try and write this down. C y dash is equal to C z dash, and here let's see, B y dash is equal to B x dash. So this part is clear. Now let's try to look at this length ax dash and az dash. What you want to notice from this picture is that ax dash plus a z dash, so a x dash plus a z dash is actually equal to the perimeter. Now that is pretty obvious, you see, because this length is equal to this length and this length is equal to this length. What you will notice is this length plus this length is the same as this length plus this length plus this length, and that is the perimeter. In addition to that, we have these two as equal, and that would mean that 2 times ax dash is equal to the perimeter, and that would mean that ax dash is actually equal to ax dash is actually equal to the semi-perimeter. We are well used to that notation. So now I have to figure a way out of putting it here. So what should I do? I think I have no option but to make some space for myself and mark this length out as the semi-perimeter. And that's a big advancement in a formula that we want to derive. Now, having said this, one immediately notices here that this length, now this length, which is bx dash, which is the same as this length, will therefore be equal to s minus, what is this length? This length is nothing but c. So it's not, I won't write it here, it's getting too cluttered up. It's s minus c. And similarly then, this length will be equal to, this length will be equal to s minus this length, which is b, s minus b. Alright, so this length is equal to s minus c, and this length is equal to s minus b. And finally, the last thing here, and since it's an important thing, let me try and change the color of my pen. Maybe I shall use blue. Okay, so now for the important last part of the calculation, what you have to understand is that this triangle here, this triangle here is similar to this triangle, and the reason is that both of these are 90 and you have a common angle, so AA. And in these two similar triangles, this length we already know is the in radius. This length is the so-called radius of the excircle, and so I can write here R divided by RA is equal to this distance, which is s minus a divided by this distance, which is equal to s. So everything is on the picture, and this is the formula that I am really gunning for, and I am done. So this was the we are done. So I hope that it wasn't too bad, and the worst possible thing is, worst possible case, you can go back to the book, but this is the real formula that we are looking for. So let me just simplify this. This tells us that RA is equal to RS over S minus A. But remember that RS yesterday for us was the area of the triangle. So area of the triangle ABC divided by area of the triangle ABC divided by S minus A is your RA, which is the radius of the excircle. And of course, by symmetry, we can write down the formulas for RB and RC, which I shall not bother to do. But I think this completes the discussion on the excircle. Like I said, I think my diagram wasn't too bad, but I would urge you to read this up from the book. We've gone through all the main ideas. Alright, let's stop this lesson here. All the best.